No? Okay, so let's start, we're really at the final stretch of what we need to do in complex analysis. And I've sort of already done a bit of this that I'm going to do today already on Tuesday. And so the idea is to like define sequences of analytic functions or understand, right? When is it that if I define an analytic function as a sequence of analytic functions, when is it that I've actually defined an analytic function? Right? The reason why this is important is that many functions are defined as a series, or sometimes you want to like write a function as a series, as a power series, but not necessarily power series, could be other types of series. And we want to know when is it that this series is analytic, right? This is we understood this for power series all the way in the beginning, right? And we said the radius of convergence for the power series, we proved all these theorems. We now have to do it basically for general sequences of functions, right? And so I sort of motivated, I mean, very briefly, but sort of, I mean, it's, yeah, I'll say a few more words about it today. This the core theorem that we'll use to understand this, right? So again, what we needed was a way to argue that if I have a sequence of functions converging to some function, right? I have to argue when is it that the function, right? So we can think of, I have a sequence of functions fn converging to a function f, right? It could be in the sort of super weak sense that for all z, fn of z converges to f, right? This is an extremely weak just pointwise sense. But I want to know what other conditions are needed in order for, if all the fn's say are analytic, to make sure that f is also analytic, right? And so, right, it's clear, it's very easy to come up with many examples. I mean, you don't even need to get to complex analysis for that, right? Even over the reals, I'm sure you've seen many examples of this, that, pointwise convergence is generally not enough. Like you can create all sorts of weird behaviors with pointwise convergence, but uniform convergence usually is more than enough. And so the question here is, what is the right? We want something weak enough that we can see it in many examples, but we want something strong enough that still implies analyticity. And how weak we wanted something that we can actually often easily prove that this type of convergence happens, right? And so the right notion in this sense, or a very useful notion, is this one of converging uniformly in compact subsets, right? And I sort of tried to describe why. The reason being that doing like what is for something to converge uniform, right? It's you have this epsilon delta things that you would get in pointwise. Uniform means that you can pick the same for every point in the domain, right? This is what uniform means in all in all the analysis, not just complex analysis. And because you're in a compact set, taking maximums and minimums and so on becomes a lot easier, right? And so oftentimes it's very easy to prove these things, and maybe we'll see a couple of examples. Okay, so let me just write the theorem then. I mean, I wrote it already on Tuesday, but it's a theorem that makes sense, I guess, to write twice. All right, so this is a theorem due to Weierstrass. So let's say I have Fn analytic in a region omega n, right? And let's say that we have that Fn converges to, I mean, I guess, yeah, I guess I'll just use this notation. Maybe it's better, right? Just Fn converges to F, right? In omega, right? So I discussed this already a little. What does this mean? Omega n might not be the same as omega, right? But what's important is that, right, for all points z in omega, right, there exists n0 such that for all n bigger than n0, z must be in omega n, right? So it's fine if there's points in omega that are not in all omega n's, but it needs to be that at least at some point, once you go far enough in n, you start being able to take the limit, right? Because the limits are all always formulated as for n big enough, so then this is enough, right? So just as a side parenthesis, right? This is what is meant by convergence in this way, right? When the sets are not the same, right? Uniformly, and what we ask was uniformly on each compact subset. Maybe I should write subset of omega, right? Okay, so then then F, wait, then F is analytic in omega, and Fn prime converges to F prime uniformly on every compact subset on each. So this is the theorem. Okay, this turns out to be sort of the most useful balance between you know, how much can I weaken the notion of uniform convergence and still get what I want. Okay, and you know, there's several ways of proving this. Okay, so proof, there's basically, I mean, okay, I tried to give already a hint of why this was true. Okay, what's interesting here? The interesting thing here is, why is it enough to ask that uniform convergence happens on each compact subset, right? That's the part that's interesting, right? And the other part that's interesting is, why is it that you know, that's a thing that we can prove for a lot of functions, right? These are the two questions that should be in your mind right now, right? One is, why is it that being converging uniformly on each compact subset is enough to get still analyticity of the limit and so on? Question number two is, why is it that actually becomes easier to prove uniform convergence over compact subsets? Like I already said something about how you can take max and means over compact subsets, right? So I already said something about this. I didn't say something about the other question that should be in your mind. I did a bit on Tuesday, and was this idea that because functions can be, a function being analytic or not, right, can be described by its behavior on integrals, on contour integrals, then right, then all I want is to make sure that convergence of, like, that the limit of the integrals of contour integrals is the right limit, right? And because contours live inside a compact subset of omega, then for sure I have right. Then for sure, you know, if I converge uniformly in that compact subset, my integrals all behave fine, and so my function is to be analytic, right? That's the core idea, and so what are two ways of exploiting this this idea, right? One is right. What are two ways that we can argue that a function is nice because how it behaves in integrals? Right, we've seen two examples of this, right? One is Morera's theorem, right? So maybe I should make a parenthesis here with another color, right? One is Morera's theorem, right? Because Morera's theorem said that if the integral around a curve is, if the integral around a curve is zero, right? For all the closed curves, right? If sort of the converse of Cauchy's theorem, then the function needs to be analytic. So it's very much in the style of the thing that I just described, at least in the spirit, right? The other formula, the other theorem that's very much of this style is something like Cauchy integral formula, right? Because Cauchy integral formula writes a function as a function on an integral, as the value on an integral on a curve around the point. And so if I prove that everything goes well with the integral, or with the contour integral, then I also get that everything goes well in the function, right? And so these are the two different proofs, right? So we'll see this one very briefly, and you'll see this one in exercise class. And in particular, this one is the right one to get convergence of the derivatives too. So you'll see that in exercise class. Or gives also, right? Morera's theorem, in the way that I'm going to present it, doesn't give that, but it's a bit simpler, and so I'll just do it here so that we can move on to other things. Right, so we're going to take the approach of using Morera's theorem, right? And now take, okay, so now take, right, A, say, in my, right, in my set omega. And now let's take a compact disk, right? So take a compact disk around A, take a compact disk, right? So let's call it, I don't know, B, like, right, some compact disk, right? This means the closure of the disk around inside around A and inside, so a compact disk around A and inside omega. Okay, so clearly there is, right, there must exist some n0 such that for all n bigger than n0, right, omega n actually contains this compact disk, right, because of the notion of convergence, right? Inside a compact disk, there needs to be I have a compact disk. I have this uniform convergence. So at some point, for n bigger than something, you need to see, right? It needs to be that omega n contains this, right? And so in particular, for any this proof is sort of almost obvious after you see it. For any closed curve omega inside this compact disk, okay, I guess I don't need to write this V, right? So okay, we have that the integral around omega of fn of z dz by Cauchy theorem is 0, right? Right. So this is by Cauchy's theorem, right? But so because of uniform convergence in the compact disk, we also have that the integral of f z dz, right, will be equal to the limit as n goes to infinity of this integral. Sorry, right? Because since the convergence is uniform, I can move it within and outside the integral. No problems there, right? And the curve, I mean, everything is in a compact set. The curve is closed, is compact, and all this. So, right? So this is equal to 0, right? So my function integrates to 0 in any closed curve inside. So it needs to be analytic, right? And so f is analytic. Analytic it's analytic in the disk. Okay, I mean, I should make the curve just be in the disk. There's no need to be in the boundary of the disk just to make things simpler. Okay, so the curve is analytic, right? And you saw here exactly this intuition that I tried to give, that because you can complex analysis allows us this amazing thing that you can measure smoothness of functions by looking at how they behave on integrals. I mean, if you think about this from the viewpoint of, say, like real analysis or something, before we learn these things, it's kind of surprising, right? But it allows us to do this. And so now you can prove all sorts of these theorems just from that idea alone, right? And so for the derivatives, you'll see for the derivatives that the derivatives converge and uniformly on each compact set, you'll see an exercise class. But I'm sure, if you find yourself with a free hour, just sit down and try to prove it yourself before you see in the book or in the exercise classes, and it's exactly what you would expect, right? You write the formula using the Cauchy integral formula, and you make sure that things behave well on the integrals, and so they need to behave well on the derivative too, right? It's Cauchy integral formula. Okay. So in particular, I mean, this theorem is very, very useful in for series, right? And this is really where it's useful. So this theorem is very useful. Okay, I should say to prove this. Okay, let me make a proper square. Theorem is very useful for series. Okay, I mean, and it's right now, if you take the series f of z, like you take, right, I'm going to use the same notation. I mean, okay, a slight abuse of notation, you'll see, but I think it's better. Right, if I take some series like this, maybe let me, and so on. Right now, I'm doing a slight abuse of, well, abuse of notation is not really the right word, but now the fn of z are not the terms in the sequence, they're the terms in the series. Okay, so I changed notation. It's not really an abuse of notation, it's a change of notation, but it's just so that I don't introduce new letters and new things. There's no need, right? It's clear. I think it's clear to everyone what's going on. Right, and so you get, if you define a function as a series, which we'll do over and over again, right? Then in fact, we did do it for, well, okay, depending, but right, the way we talked about, exponentials and trigonometric functions and so on, like we looked a lot at the series, right? But because they were power series, then we had those nice theorems for convergence of power series, so we didn't need this sophistication. But now if you want to define functions whose series are not necessarily power series, right, then we need this higher level of sophistication. And if you've looked at the homework sheet, then you see things like there's questions there about things like the Riemann zeta function and so on, in which these things become important. Okay, then if the series, if it converges, right, it's very useful for series. So if we have this, and if the series, let me write the series, right, converges uniformly in every compact set, in every compact subset of like of omega, say, okay, okay, then F, right, is analytic, right, again in omega, of course, and the derivative F prime, and the derivatives converge, the derivatives, let me write it this way, derivatives can be taken term by term. I mean, this is how the language we used also for power series, term-wise. Okay, so what I mean by this, I mean, if anything is not clear, please ask. But what I mean by this, of course, is that, if the series converges uniformly in every compact subset, right, then from the theorem above, this is like, there's nothing to prove, right? This is just a corollary of the thing we saw above, right? So if the series converges uniformly in every compact subset, then, this object is analytic, right? And the derivative of the sequence, the derivative of f, the derivative of the sequence converges uniformly in compact sets to the derivative of the function. But what's the derivative of the sequence here, right? If I want to take the derivative of the nth term, the nth term of the sequence is just the sum of the first n terms, right, of the series. And of course, the derivative of a sum is the sum of the derivative. So it basically is just saying that the derivative of f is the same as the derivative of f1 plus the derivative of f2 and so on. So I have a series for the derivative, right? This is just exactly the same. Okay. So now I want to just make a point. I mean, there's going to be no proof here, but the point is that, okay, so let me make like a comment, right? So we're going to make a comment now, or remark, right? So let me, so we're going to make a remark, right? That establishing, showing or establishing uniform convergence in a compact set is often easy. And there's nothing like seeing a few examples, right? So you'll see maybe some of these examples in exercise class, in the homework and so on, or you can just, try to work out a few of them. But establishing uniform convergence in a compact set is often easy. And I mean, there's a few ways of thinking of why this is easy, right? Taking maximums and minimums over compact sets is often easy, right? You also have stuff like, the covering things that if you have some kind of covering, if you can somehow cover with different rates, then you have a finite subcovering and things of this type. But even more important, perhaps, in complex analysis is because of the maximum principle, right? Because the functions in question are all analytic, the maximums of everything sort of happens always in the boundary, right? And so you get this statement that, uniform convergence, right, for compact sets, right, say for compact sets, right, uniform convergence on the boundary right, will imply uniform convergence on the set. right? And this is just because of the maximum principle. I mean, one way to view this, I highly recommend, sitting down and like convincing yourself that this is true by working out. You can prove this like in great detail, of course. But the reason is that, since basically the reason, okay, a reason, and I think from the reason you'll right away see of why this is true, and then it's a useful exercise certainly to just sit down and try to prove this very, very carefully. But it's that if I take two functions, like if I take n and m, right, some integers, say, okay, let's say natural numbers, right, and if I look at, right, if I think in terms of Cauchy sequences, and if I take a look at this, right, in Cauchy sequences tells me that I have to understand, like I have to be able to bound, right, terms like this, then this is maximized in the boundary, right? Because Fn and Fm are both analytic, so the difference is also analytic, is maximized in the boundary, maximized in boundary, right? Exactly by maximum principle, right? And so this is the reason, right? So if this thing goes to zero uniformly in the boundary, then it also needs to in the inside, right? Because the maximum is attained in the boundary. Okay, so with this, I hope to have convinced you of the two core things related to this theorem of sequences, understanding sequences and limits of functions, right? One is, why is it that uniformly on compact sets is enough, right? And this you saw via the proof. And second, why is that that's a useful weakening of of just asking for uniform convergence everywhere, right? And the reason here is, I try to convey this by saying that I think this is a good way of conveying that for you. You maybe will see actual examples where you'll see this by trying and seeing that you have to work a lot less. And oftentimes it's just not true that it converges uniformly, everywhere. But here it's already hinting that, over compact sets, things are easier, right? We could have asked uniform convergence over any subset or over any other kind of subset, but compact subsets sort of make sense because it becomes easier to argue uniform convergence. Okay, so maybe is there any questions? If there's any questions, please interrupt. I see, like, there's a chat I see from YouTube. And someone asked which page we are. Sorry that I didn't see this earlier. I'm not sure, but if you have the PDF open, just look up Fireside's theorem. Better yet, look 176. Okay, thank you. 176. Okay, I'll write here in case person sees. Okay, so we're around page 176, and there's a theorem actually on alphas. That's a very nice theorem, but I won't prove it here. The proof is simple. I think it's something very nice for you, for you to think about. And so let me just actually let me write the theorem, and I'll post it as a voluntary homework. Because it's also, I don't know, to me it's also a very striking statement. But by now we've grown, used to striking statements, I think. So maybe they become less striking with time. But yeah, so this is the theorem, and this is around those pages in Alfred's too. So let's say that I have fn of z, right? The function, I mean fn, I don't need to say of z, just fn. Let's say it's analytic, and different than zero, in a set. Let me do this, right? In a region, okay. And every time I write omega, I mean a region, but let me write in a region. Okay, and let's say, that fn of z, fn converges to f uniformly on every compact subset. Here, the regions are always the same fixed region, so it makes things simpler. Every compact. I don't actually know if that can be relaxed. I have to think about it. Okay. Then we have either. Okay, so what is the theorem trying to ask? It's trying to ask, the function is never zero. Can the limit be zero? Okay, so can the limit be 0 is the question. Of course, the limit can be 0, right? I can take like f of n equals to the constant function 1 over n or something, right? Of course, the limit can be 0. And so it's definitely possible that f of z is equal to 0 for all z in omega, right? I mean, just take the function, f of n equals 1 over n. What it can't happen is that it becomes 0 in some places and not 0 in others. So one of two things happen. Either it's 0 everywhere or it's 0 nowhere. And this is quite striking, I think. And so the proof, like voluntary homework, I mean, I guess all the homework is voluntary, but homework, okay, and yeah, but try to do it before looking up, right? Before looking up on the book. Right, I'll tell you the core idea so that you can try before you look it up on the book. It's that, right, it's to use okay, let's say that the function is not, I'll tell you the idea, and then I think is an excellent exercise to like sit down and try to prove this. So the idea is if f is not exactly 0, like f is this limit, right, we know is analytic. If f is not 0 in all of omega, right, then we have this theorem that we can go around the circle and count the zeros, right? And so what we have to argue is that when we go around the circle, say around a point, right? Okay, maybe I should be a bit more clear. Let's say, right, let's say that 1 doesn't happen and we're in 2, right? So f is not identically 0, but imagine that if 1 doesn't happen, we need to prove that we're in 2. Let's say we were not in 2. So this means that there exists, right, some z0 in omega such that f of z0 is 0, right? But f is not identically 0. Right? This is the case that we have to rule out. Right? We need to like rule out this. We need to argue that if we start with this, we get into nonsense. Okay? Like contradiction. How do we do this? Remember this formula to count the number of zeros by integrating around the circle. And because the number of zeros is 0 for all the fn's, if we can argue that the integral behaves nicely, then it needs to be also 0, the number of zeros in f. And so we get immediately what we want. Now the problem is, if you remember, the integrals look like things like this, f prime over f, right? So one needs to make sure that these integrants still converge uniformly, right? But we're dividing by f, so issues could arise. And so you just have to argue, by compactness and so on, that issues like this do not arise. Okay, so this is the idea. Try to prove it before you look it up on the book. Okay? And on the book, I guess if we were before on page 176, must be like 177, 178, something like this. Okay, so the goal here is to rule out this. And this is a striking, and useful statement. Okay. Okay, so finally we get to talk about, I think, let me look at my notes to see if I'm forgetting anything. I don't think so. I think now finally we get to talk about Taylor series, which is a long time coming. Okay, so we've been for 3 months or more waiting to see to get a statement about Taylor series. We're finally here. Okay, so that what we want to show is that f has a Taylor series, right? If f is analytic, then f has a Taylor series with a certain radius of convergence, right? This is one of the core, amazing things in complex analysis. And so this I'm gonna show today in the rest of today. So take right, let's recall. Let's do a bit of recalling. So recall that if f is analytic in a region omega, and there's a point z0 in omega, then we have the following, right? This was this truncated Taylor, I guess, sum rather than series that we saw, right? Then that f of z is equal to f of z0 plus f prime of z0. I mean, yeah, maybe the best way to write to see what the rule is like is to write like this, right? Plus, I guess, f2, right? The second derivative at 2 factorial z minus z0. I might be writing too many terms. Let's see if I have space still. Oh, I forgot. Plus, right? Plus, and okay, Taylor's series will tell me that I can just take this sequence to infinity, right? You've already seen these kinds of theorems in real analysis. What we had wasn't quite that. We had that we could always write it this way, in which there was an analytic function, right? And we didn't, all we said was that this function was analytic, right? So, I mean, clearly now it's kind of clear what's going to happen, right? I'm going to call this my sequence, so this we had already, right? Where fn plus 1 of z is analytic and actually was even given by some kind of integral formula, right? And so this is exactly what we're going to use, right? But it's clear that I'm going to just call this, right? I'm going to call this my gn of z, right? And we're going to prove that, gn converges to f uniformly on every compact subset, right? And then we're done. Subsets, or some, on some compact subsets of some, maybe not necessarily of omega, but subsets of some region. I'm not yet ready to say which region. Okay. And this will give me the Taylor series, right? That's the plan. Is the plan clear to everyone? If anything is not clear, please interrupt. Okay, so how are we going to prove that this convergence happens? I mean, now it's also kind of clear. We have to understand, to somehow bound, like control this term, right? Because this term is the difference between my gn of z and f, right? So the goal will be to control this term, right? This is what we have to do, right? So we had already a formula for what this term was, right? Given by, okay, so someone asked if, no, so here, I don't remember now what, I don't think I have to, okay, I think there's a confusion. So let me say something, and then you can tell me if the question still applies or not, and then I'll answer it. Maybe that's better. So here I'm not saying that, I haven't yet written the Taylor series. The Taylor series will be this part there underlined in black, continued. So the term n plus 1 will be, f to the n plus 1, z0 over n factorial, z minus z0, n plus 1. Completely agreed. But now I'm trying to, what we never proved this though. What we did prove is that there is a certain truncated version of Taylor series, right? The Taylor sum, if you will, where f of z can be written in this way. And then the rest of the, written this way up to degree n, and then the rest is given by a function basically that has a 0, an analytic function that has a 0 of order n plus 1 at z0. Right? What's the natural way of writing this is to say that it is some analytic function, right? This guy's analytic. At times okay, maybe this is like adding too many letters, right? But something nice, an analytic, and here a term that makes sure that it's quite small, close to z. Close to z0. Of course, this one could still explode, right? Be so big that it, I have to be able to control it, but at least it tells me something about the order of the 0. Now, I don't think, now one could have defined, of course, this f of n plus 1 with a term like 1 over n plus 1 factorial, but I think the way, like I don't have to, and I don't think I missed here by mistake. It would be the same. It would just be another definition of fn plus 1. But I think this was the one we gave. Okay, thanks. Yeah, thanks so much for the question. Yeah, it's important that this is all clear, and questions are the best way of making sure that things are clear. Okay, so the goal is to control this term. And how do we do this? Well, we had a formula. When we developed Cauchy integral formula and so on, we worked out formulas for these functions, right? And the formula we had was that fn plus 1, right? This is also something we had from before, was equal to 1 over 2 pi I integral over c of xc over x minus z0, right? N plus 1, c minus e, right? For over some circle, like basically for any circle C, such that the corresponding disk, meaning the disk inside corresponding disk has that the boundary of the disk is inside omega, right? Because I need to be able, right? I have some, let's draw a picture. Right, I have some omega, and now there's some point z0, right? I need to take a circle such that the interior of the circle, right, the corresponding disk, the closure is still inside the set, right? And so what we're going to do, I don't want to take, I've been, taking extra minutes from you a bit too much, so I just say next step, right? Next step, right? It's to bound this integral, show that it's small enough that you get the convergence. Okay, so we'll do this on Tuesday. Okay, yeah, thanks so much. And if anyone wants to stick around, I'm very happy to. Blue. Oh, someone asked. Okay, sorry. Yeah, I wrote so. For any circle such that the corresponding disk, I guess, satisfies. I mean, this is a fancy way of saying that the circle and the inside of the circle is in the circle and the inside of the circle inside omega. Right? I mean, this is the same thing as saying C and inside of C is in